Hello, and welcome to Rules for Exponents. This is an intermediate algebra look at exponent rules, so we're just going to go kind of some less challenging examples. I'm not going to call them easy by any means, but for a little more challenge, way more challenge to the problems, check out my college algebra lecture on exponents as well. So we use exponents as shorthand notation for repeated multiplication. All right, think about the order of operations. Our order of operations are parentheses, exponents, multiply, divide, add, and subtract. And I usually write it like this because multiply and divide and add, subtract together in pairs, they're on the same level. So repeated addition is multiplication. Repeated multiplication is exponents. Repeated subtraction is division. All right, so they're lined up kind of on top of each other. Every exponential expression has two parts. The base, which is, in this case, 2, and it's the number that's repeatedly multiplied. All right, that's what we multiply over and over and over again. And the exponent, which tells us how many times to multiply. Okay. Let's take a look at the product rule. If we have x to the m times x to the n, this is the same as x to the m plus n. So when multiplying exponential expressions that have the same base, we're going to add the exponents, and here's why. Let's throw out a little example here. Let's just take x squared times x cubed. Think about what x squared is. That's x times x. Think about what x cubed is. That's x times x times x. Well, what do we have here? We have x 5 times. And so 2 plus 3 gave us the 5. If we were to write it out, we get x to the 5th. Fantastic. When dividing exponential expressions that have the same base, we're going to subtract the exponents, and it's always exponent of the numerator minus exponent of the denominator. So for example, x to the 7th over x to the 4th. Why would I do that? 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4. These 4 can cancel out these 4 x's, and I'm left with x to the 3rd. And what do you know? 7 minus 4 is 3. So that's where these rules come from. Again, if I had x squared cubed, that's x squared times x squared times x squared. But an exponent, right, repeated multiplication of things with the same base turns into addition of the exponent. So definitely a difference between product and power rule here. Okay, so let's use some of these rules. These are the big three: product, quotient, and power rule. And check this out. If you are multiplying two things with the same base, you add their exponents. Right? This is the product rule. If you are dividing two things with the same base, you subtract their exponents. That's the quotient rule. Power rule: an exponent to an exponent. So if you have an exponent raised to an exponent, you're going to multiply it. So this order of operations kind of helps us step down one. So stepping up is the shorthand notation for the previous one. Stepping down is exponent rules. So that's something that we carry with us, right? We all know the order of operations. It helps us remember our exponent rules as well. So when we're looking here, to simplify, 4w to the 6th x squared times 8w x to the 9th. Because everything's being multiplied, I'm going to multiply 4 times 8 and get 32. I'm going to look at this w to the 6th, and I'm going to look at this w to the 1st, right? If the power is not written, it's assumed to be 1. 6 plus 1 makes a w to the 7th. I'll have an x squared and x to the 9th. I have 9 of them, and I add 2 more. That's going to be x to the 11th. All right, so if we're multiplying two things with the same base, we add their exponents. I'm not multiplying this x squared times the 8 necessarily. I'm combining our like terms here. It looks like I messed up that 9 a little bit. There we go. With division, I sometimes kind of space them out a little bit. And instead of equal signs, I'm going to use an arrow. So I'm looking at 40 divided by 5. I'm looking at t to the 11th divided by t to the 3rd. And I'm looking at w to the 14th divided by w to the 9th. So we look at each kind of pairing individually, just like we did with the number and the number, the w's, then the x's. 40 divided by 5 is 8. T to the 11th divided by t to the 3rd, that's t to the 11 minus 3. W to the 14 divided by w to the 9, w to the 14 minus 9 if we wanted to write an intermediate step. And this is 8t to the 8th, w to the, that's minus 9, so that's a 5. Okay, so we look at them individually. The 24 and 14. When I simplify those, it looks like I'm going to get 12 over 7. When I simplify b to the 18th and b to the 10th, it looks like I'm going to get b to the 8th, right? 18 minus 10. And c to the 4th over c cubed, 4 minus 3 is 1. So you could write 12 sevenths, b to the 8th, c to the 1st. This is a fine answer. You can write it like this. You can write it like this. As long as the b to the 8th and the c are not in the denominator with the 7, it doesn't matter if the fraction is next to it or if the denominator is under all of it. But as long as the variables do not somehow magically go to the denominator, this one's good. So now we have more rules. In raising an expression to a power, that power can be applied over multiplication and division. So I'm going to write this order of operations again, PEMDAS. If we're multiplying two things with radicals, there is a step down. It's possible, so it's all good. But notice there's no way that we could step down if we're at add and subtract. So if it's x plus y to the m, can't do anything about it. X minus y all to the m, can't do anything about it. But because multiplication and division are not on the bottom level, we can simplify those. So here we go. So 3x to the 5th, y squared, z to z, and then all cubed. According to this rule of products of powers of products, order matters, I'm going to have 3 to the 3rd, x to the 5th to the 3rd, y squared to the 3rd, and z to the 3rd. My 2's look a lot like z's, so I'll always cross my z's. 3 to the 3rd, 3 times 3 is 9, 9 times 3 is 27. Remember, a power raised to a power we multiply, so that's x to the 15th. Power raised to a power we multiply, 2 times 3 is 6, so that's y to the 6th. And even though this z does not have an exponent written on it, it's assumed to be a 1 because it doesn't have any other exponent. 1 times 3 is 3, I'll have z to the 3rd. All right, 27, x to the 15th, y to the 6th, z to the 3rd. In number 2, we're going to use the powers of products and quotients at the same time, because this 2, this squared on the outside, is going to everything in the numerator and everything in the denominator, using the quotient, and then inside the numerator to each of the terms, using the product rule. So here we have 4 squared, m squared, p to the 8th squared. 5 squared, m cubed squared, p to the 5th squared. So I didn't do any simplifying ahead of time. Probably should have, but I just didn't feel it. Wasn't there for me. So it wasn't the first thing I thought of. But I will show you one where we do simplify inside first. So 4 squared is 16, m squared. A power raised to a power, 8 times 2 is 16, so that's p to the 16th. 5 squared is 25. A power raised to a power, so m to the third squared, 3 times 2 is 6. P to the fifth squared, 5 times 2 is 10. Now, a little bit of a trick I have, and it still uses that quotient rule from the first page, but notice the 16 and 25 have nothing in common. So this answer is definitely going to take on the form of a fraction. But let's look at these m's. I have 2 m's in the numerator, and I have 6 m's in the denominator. The denominator has more, so that's where my answer goes. How many more? 4 more. Right? There's 4 more m's in the denominator than there are in the numerator. So the denominator has more, that's where we'll end up with our answer. This m to the fourth will be in our denominator. If I look at the p's, p to the 16 over p to the 10, which has more? The numerator has more because 16 is bigger than 10. How many more? 6 more. And so we could simplify at the end just as easy as we could have simplified at the beginning. And even though I didn't necessarily use the quotient property, I kind of did. Let's put this as an aside. The quotient rule says that if I'm dividing two things with the same base, I subtract the exponents, numerator minus denominator, so 2 minus 6, negative 4. This negative is a direction sign. If it's positive, it stays where it is. If it's negative, it goes the opposite place in the fraction. So you take it across the fraction bar. So that's how we get m to the fourth in the denominator as well. I like the idea of comparing it. This is usually for students that have difficulty with the negative and how does that happen. I like the comparison method, but it's still technically correct as well. All right, let's look at number 3 here. So we'll have a 3x squared y to the fifth times 2x cubed y all to the third. But only the second parentheses is to the third. So I need to handle that first. So I have 3x squared y to the fifth times 2 to the third, x cubed to the third, y to the third. So I take care of that outer exponent, the exponents raised to the exponents first. And let's simplify that. 3x squared y to the fifth, 2 to the third, 2 times 2 is 4, 4 times 2 is 8. A power raised to a power, I'll have x to the ninth, y to the third. And now, just like in our first example, we can multiply 3 times 8 and get 24. X squared times x to the ninth, we get x to the 11th. Y to the fifth times y to the third. Multiplying two things with the same base, we add their exponents. And we have completely simplified this exponential expression. All right, now here's that negative exponent rule. Right, x to the negative n is the same as 1 over x to the n, and I kind of showed you that above. 0 as an exponent. As long as x isn't 0, x to the 0 power is 1. And I frequently say anything other than 0 raised to the 0 power is 1. And if you want to know what 0 to the 0 power is, you need to keep studying and get on to calculus, because calculus will help us talk about why that's such a weird thing and we can't really determine the answer. It's called an indeterminate form, in fact. We also have rational exponents, so we could use rational numbers as exponents, and that denominator goes in the little check mark part of the radical symbol. That's called the index. The x is called the radicand. It's underneath the radical, but we'll get into that in more detail in a later video. Okay, so g to the 4/9, that way we could all see it. The denominator goes inside as the index of the radical. G to the 4th will go inside. My 9's and my g's look a lot alike. m to the 7/10. I like these sideways fractions better sometimes. The 10th is the index. M to the 7th goes inside as your radicand. That's it. That's the whole thing right there. We don't have to simplify that at all or any further. All right, we're just rewriting in radical form. I gave us way too much room there. Okay. If we simplify 9a to the 6th, b to the 10th, all to the 0, it doesn't matter what it is. If it's all to the 0, it's 1. As long as a is not 0 and b is not 0, we should be good. It could be house. Raised to the 0 power is 1. That's it. If it's raised to the 0 power and it's not 0 to start with, the answer is 1. All right, so negative exponent. I was going to scroll up, but I decided I'd point at this. X to the negative n is 1 over x to the n. So we think of this frequently as a reciprocal. A reciprocal, there we go. The reciprocal means just flip it over. So if we take it across the fraction bar, the exponent becomes positive. So there's a couple of ways we could look at this. We could use the power property of quotients. Make sure that negative is there. And then we use the negative exponent rule that says I take it across the fraction bar to become positive. This 3h to the 4th is to a negative 2 in the numerator. So 3h to the 4th will be to a positive 2 in the denominator. So we could flip the fraction over, take the reciprocal, and now we'll use the power over products. 2 squared, p to the 7th squared, 3 squared, h to the 4th squared. 2 squared is 4. 7 times 2 is 14. 3 squared is 9. And 4 times 2 will give us h to the 8th. All right, a single p term, a single h term. I don't have anything I need to simplify. The 4 and the 9, they have nothing in common. They can't simplify either. There's several different ways of going about these problems, and I'm really only going to show you one way on each example. I might use different ways on different examples, but there's several ways you could go about doing this particular problem. And I guess I'm not going to show you multiple ways of doing other problems, because that's my last example for this video. Basic rules of exponents. That's it. Thanks for listening.